Hey, hi everyone. Welcome to our next Saphir regular webinar. I am very pleased to have with us today James Beacham. He is the founder of the long-lived particle community at CERN and beyond. He is a member of the Atlas collaboration at CERN. He is also a member of the Methuselah collaboration, which is a new proposal for novel lifetime frontier experiments. James is also a very passionate science communicator. So I'm really happy, James, that you accepted our invitation. Thank you so much. And we are eager to hear about new discoveries at the LHC. Please go ahead.
Thanks so much. Well, I wish I were going to tell you about some new discoveries. That would be pretty fantastic. But alas, of course, the question posed in the title is a big one. It's an enormous one. So yeah, first of all, thanks very much for the introduction and thanks for the kind invitation to give this seminar. I admit it would be fantastic if we were all to be in the same place at the same time, for example, in Chile, which I've never visited. I'd love to come at some point. But this is also fantastic. I'm really thankful for the invitation to give this talk. And the title of the talk, as you can see, and as Giovanna said, is Where Are the New Discoveries at the Large Hadron Collider? So, but of course, it could also be titled, let's see, where's my thing? It could also be titled, Where Are the New Discoveries in Collider Physics in General? Because the LHC, while a very prominent project, is of course only one component of the broader global search for physics beyond the Standard Model. And so beyond the Standard Model, that's what we're all seeking. And we're looking for some kind of, chink in the armor of the Standard Model that could lead to an explanation to any of the big open questions of physics, related to dark matter or the antimatter asymmetry of the universe or the relative weakness of gravity, among many others. But the truth is that right now we are living in a very strange time period, in fact, in the history of physics, particularly compared to recent history, because throughout the entire 20th century and into the first part of the 21st century, physics progressed via a nearly unbroken string of big theoretical hints followed by big experimental discoveries. So you think of the discovery of the J-psi particle or the predictions of the W and the Z boson masses, et cetera, right up to and including the discovery of the Higgs boson in 2012. And so before the LHC turned on, we had these, excuse me, we had these electroweak fits that people were doing. And we had data from LEP that putting this stuff all together, it kind of suggested and hinted that something might be just around the corner in energy. And alas, it was true. But 2024 is very different from 2011. Right now, we're left with enormous open questions, the answering of any of which would be revolutionary, but with zero big hints. And if someone wants to argue with me, I would be happy to argue about the lack of big hints here, but we don't have them. Supersymmetry has thus far not appeared at the LHC, nor large extra dimensions, nor vanilla WIMP dark matter, et cetera. And it's true that we do have a handful of modest anomalies and deviations. So where is the next discovery going to appear? Will it be something to do with the G-2 of the muon? Or will it be one of the little bumps in the various two-object spectra, and one of these will turn into a scalar resonance, some of these at the LHC? Or perhaps in this funny business with the W mass, or perhaps in the Z decay asymmetries, or multi-lepton anomalies, or flavor anomalies, or something else entirely? Or will it actually appear at larger colliders in either precision measurements of the Higgs or higher energy proton collisions decades from now? The truth is that none of these is any more well-motivated than any other or likely to lead to a discovery than any of these others. And while you and I understand that the shift in the mindset that collider physics has undergone in the last, say, 12 years is real, and we understand that the real task of particle physics is, we understand what it is, this attitude is unfortunately not universally shared by those outside the field. And I'm not even going to talk about the kind of anti-science trolls who are somehow allowed to write the same article over and over for outlets like the New York Times or the Guardian about how collider physics is a fraud and the LHC is a failure. I'm not even going to talk about those. But there are others much more sober who also basically misunderstand the task of particle physics. So, for example, I read an article, I forget, when, sometime in the last couple of years, that quoted a prominent non-collider physicist and Nobel laureate as saying, quote, "If they don't find anything else at the LHC, they're finished," end quote. To which I audibly replied after reading this, I think in a train somewhere, "Excuse me?" Because this is strange. It's a bizarre thing to say because, as I mentioned, this evinces a misunderstanding of the task of collider physics. So what is an experimental particle physicist? The truth is that particle physicist is not a particle hunter, but is in fact a cartographer. And the task of particle physics is not to find supersymmetry, and the task is not to find dark matter, but to rule out all the possible places where a discovery, i.e. a deviation from background, could be hiding. So in this sense, particle physics, particle physics is the task of particle physics is to look everywhere with all experiments, both existing and future, without theory bias or favor. So the task is to look everywhere. And don't get me wrong, I love theories and I want all of them and the new ones too. But experimental physics is really a process of cartography. So in this talk, I'm going to give you a survey of the various ways we're doing cartography physics at the LHC, and then I'm going to extend it to CERN in general, and then touch a little bit upon the broader global search for physics. I obviously won't cover everything, but I want to give you a flavor of the rich tapestry of exploration that's occurring right now to mix, I think, 3 metaphors there in a row. That was nice. So we can start with the LHC. I hope I don't need to explain what the LHC is to anyone here, but just in case someone is new, and of course, new people are welcome at all seminars that I give. The Large Hadron Collider is a 27-kilometer circular tunnel about 100 meters underground on the border of France and Switzerland. And in this tunnel, we use superconducting magnets colder than outer space to accelerate protons, to almost the speed of light. And we smash them into each other, 4 points on the ring, briefly recreating the conditions of the universe as they were, just a fraction of a second after the Big Bang, 13.8 billion years ago, because understanding what was happening back then will help us explain the universe we have now and could help answer, in principle, some of the biggest open questions of science related to, like I said, dark matter, the antimatter asymmetry of the universe, the relative weakness of gravity, and more, other things we can touch upon, dark energy and things like that too. So this is really what the LHC is. And in fact, at the end of the day, what it is it's a big data exploration machine. And so this is a plot of the total integrated luminosity delivered by the LHC in yellow and then in blue, and then in yellow collected by the CMS experiment over the entire run of the LHC. And from this data, the ATLAS and CMS experiments have published hundreds of disjoint analyses of the nooks and crannies of this data, searching for BSM physics. So just by the numbers, it's a wildly successful program. Yes, of course, none of these have shown a discovery, but of course, this is cartography physics. And so every single one of these is a great success. So this is a heroic amount of data and hundreds of published BSM searches. It's a wildly successful program. And of course, ATLAS and CMS are only 2 of the 4 central detectors of the LHC, the other 2 being ALICE, which was designed to study heavy ion collisions and phenomena like the quark-gluon plasma, and then HCB, designed for precision measurements of B hadrons, but of course, they can do fantastic things related to BSM physics as well. And so right now, we are in fact right now in the middle of what we call run 3, as you know. So this is a screenshot of LHC page 1 from just a few hours ago. Stable beams, very nice. Every experimentalist likes to see that. And of course, you can check this yourself anytime you want as well, the link at the bottom there. And so with all of those searches that I mentioned and those papers published by ATLAS and CMS, so what do these papers say? So how do we search for, what do we search for with ATLAS and CMS, and how do we think about these searches? And I'll focus on ATLAS first because I work on it, but the story is similar at CMS. The BSM program at ATLAS is rather vast. We search for dark matter, supersymmetry, miniature black holes, BSM decays of H125, vector-like quarks or leptons, dark photons, heavy neutral leptons, new high-mass gauge bosons, exotic scalar cousins of H125, flavor anomalies, etc. And this is not to mention any of the other, the wide program of standard model measurements that are done, looking for, measuring very precise things about the standard model that could also lead to potential deviations that could then be observations that lead to the new discovery, et cetera. So the et cetera has an enormous number of things in there. So for example, and I'll just go through a few of these as we get into things. So for example, dark matter. We can search for dark matter with ATLAS. And so dark matter is, of course, neutral, so we'll never detect it directly at the LHC, but there are several ways that we can infer its presence by measuring, for example, missing transverse momentum. If you have a proton collision and you see 2 things going in one direction and basically nothing going in the other direction, this could infer the existence of a neutral particle that carried away a lot of momentum. Or we can, for example, look for detectable decays of a dark sector mediator. In fact, dark matter, if it's expected to be, say, the GeV range for the particle itself, for the dark matter candidate, We're not necessarily going to be very good at making those and detecting them in the LHC, but the one thing we're really good at the LHC, if they exist, is making high mass gauge bosons. So, for example, you could have some kind of dark sector mediator in the hundreds of GeV, TeV scale, and we can make those quite well and detect the decay components. Then, of course, you can also look for more complex dark sector constituents as well. And so you can see we perform a wide variety of these searches with no discoveries so far, of course. And at the end of the day, we can, in fact, compare these results from the LHC with those of direct detection experiments, dark matter experiments, so in plots like these. So the LHC collides protons, so we can convert these dark matter limits to limits on the dark matter nucleon interaction cross-section that's used by direct detection experiments. And you can see that under different sets of assumptions for coupling constants, which of course don't know the real values, the results are nicely complementary to direct detection experiments. So again, this is very nice. This is a nice example of cartography, which is mapping the territory. But distinct in idea and concept from dark matter is, of course, the Higgs boson. So we know that something exists, which is H125. We discovered this. And we know that the current limit on the invisible branching ratio of H125 is about 10%. And we'll never get it to very, very low at the LHC for the entire run. And we also know that extended Higgs sectors, that there are many of them exist, that yield plenty of 4 standard model final state topologies that can be searched for. And in fact, we do this. So these are summary plots of limits from searches for H125 decaying to 2 BSM particles, here denoted A, and each of which then decays to standard model particles. And you can see the kind of tabulation of the various final states that are looked for in various searches. So, these are summary plots. And then this kind of behavior appears in standard model extensions, like I said, such as in this example, something called the 2HDM plus 2 Higgs doublet model plus S, another scalar model. And so like in the dark matter case, there are certain things we don't know. So there are various assumptions you can make about the couplings and the orderings of masses in these theories. And then you can make different types of plots. And so on the y-axis here is a quantity that is a ratio of the Higgs cross-section to the standard model cross-section times the branching ratio of the Higgs into these two particles, the 2 BSM particles. So once this gets below 1, you can start to say something non-trivial about the potential branching ratio of this H125 to this BSM particle. So these are really interesting plots, and in fact, I'll make a kind of interesting one here. So these in fact need to be updated. These are from March of 2021. There are some new searches that come in here. For example, this orange line was one component of my 3-experiment PhD thesis that I graduated back in 2014. And so this has been updated recently by an Atlas search, which is really, really nice. I encourage all of you, if you haven't had a chance to look at it, look for the Higgs to 4 photons analysis from Atlas, which is very recent. It's very nice. Physics is one of the places where we like when someone updates our result from the past and gives us new information, even though mine's not necessarily obsolete. It's now been superseded by this one, and I think that's a good thing. So we also, of course, look for supersymmetry. And so don't listen to the haters. Supersymmetry is not dead. Supersymmetry is simply one more generically well-motivated property of spacetime that our universe either does or does not use. We just have to look for it. It doesn't matter. There's a lot of, it's funny to me how there's a lot of emotion that's tied up in supersymmetry over the years. And I think it's very strange from an experimentalist standpoint. It either does or does not exist, and it's fascinating to look for. And this very simple postulate, this new symmetry between bosons and fermions, leads to a wealth of detector signatures. And so we will be looking for this for the rest of the LHC and also future machines. And the nice thing about this is that it leads to these wide variety of searches we can do. So you can see from these summary plots, we have a large number of these searches in Atlas. And on the left is a bar chart of the lower limits on masses of new SUSY particles from a bunch of different searches. And we're reaching the edge of, the kind of kinematic edge of mass ranges for many of them, because of course we can't increase the energy of the LHC. At least much more than what we have right now, 13.6 TeV. And then the y-axis is the mass of a SUSY particle, kind of the mass scale of the thing in question that's being searched for that in that search. And on the right is a plot, one of the many different types of plots. There's a link there to the summary plots. I can provide these slides later. And this is, on the right is a summary plot, or a kind of combination plot of limits from several different searches where the y-axis is the mass of a SUSY particle here denoted chi1, and then the x-axis is the invariant mass of chi1 and chi2 and other SUSY particles. So you can see, and this is charged, this is a charge, chi1 in that case is a charge that's different, it's a different chi1. And you can see that again, that these exclusions are indeed cartography. This is map making. And so these are just 3 examples of classes of searches at the LHC looking for particularly well-motivated decay, particularly theoretically motivated decay topologies. But wait, I mentioned at the beginning of the talk that the task of particle physics is to look everywhere without theory, bias, or favor. So is this really the best way to think about the LHC? Think in terms of dark matter or the Higgs boson or supersymmetry. So we have no big hints anymore. We have no guaranteed discoveries. If we think strictly from a theoretically motivated, quote unquote, mindset, we limit ourselves. So it seems that we're looking everywhere, but what could we be missing? Okay, so this is how we really need to change our mindset in the field. And luckily this has been happening. But we really need to make sure that we keep in mind that this mindset shift is happening right now in front of us. And we're moving from a signature, when we think about a model first and then come up with a search for that model, when instead we should look what kind of signatures can we be sensitive to at the LHC, and then think about what a model that might if you want some kind of benchmark model for that signature, that should be the second case in your mind. Or this is also known as, what could we be missing? Because again, from a cartographer mindset, I need to not just necessarily go through all the different types of nooks and crannies of supersymmetry parameter space, which is rather vast in and of itself. I need to make sure that I'm not missing topologies and signatures that could generically lead to deviations. Again, the task is to look everywhere, right? And so we look at, really it's anomaly detection, it's a deviation detection. We need to understand the backgrounds everywhere first, and then see what could be a deviation from that, which could then lead to a discovery. So if we shift our brains this way, it means that we have to shift away from thinking about, the standard way that we think about new physics X at colliders. So typically we think in terms of the stuff that I've been talking about, the mass of the particle, you can't go much higher up in mass above some kind of kinematic limit unless you go to a much higher energy machine. So the way you could find a new particle is, go to a higher energy machine, which opens up new mass territory for direct production and detection and outright discovery. Or you need to take a large amount of data and take more data, and then you can get a better limit on the cross section, or be sensitive to, the same way of saying that is be sensitive to very low cross sections. And that's typically what we think about when we think about new physics X at colliders. And this is definitely what they were thinking about when the LHC was being designed. But if we think about it from a different way, there's a different axis here. If we think about it instead in terms of the mass of the new particle and then the lifetime of the particle, in this case denoted as c tau, what this leads to is we realize that the overwhelming majority of the work of collider experimentalists has been focused on stuff that's down here, which we refer to as prompt, or stuff that's stable and that has escaped the detector. But that means that we're basically overlooking an enormous part right in the middle, which could be a discovery and that could be hiding there. So of course, what this means is that we can in fact make sure that we need to make sure that we're sensitive to so-called long-lived particles as well. So this is this is what we refer to as the lifetime frontier. And of course, if this is something that I have experienced firsthand back at the beginning of the LHC when it turned on, there are a few people that were looking for so-called long-lived particles, but you would always occasionally, you would typically hear someone at some point say, yeah, I don't know, it's kind of interesting, but how well motivated is it really? And the answer is that it's generically well motivated because, for example, the standard model is filled with long-lived particles. So this is a plot from the long-lived particle Bible that Giovanna was a key component of with me and Brian and the rest of the crew back in the day. And Brian made this plot that's showing that, and I added some ameliorations here and some other things from Simon Knappen, et cetera. That if you just use naive dimensional analysis, the particles in the standard model should have their lifetimes that lie along this little peach-colored line here. But something almost always steps in, some kind of quantum field theoretical thing steps in that leads to a lifetime that's different from this value. And of course, how do we get particle lifetimes? The proper lifetime tau of any particle is given by the inverse of its decay width or decay rate gamma. And so this is the probability per unit time that it will decay. And so if you need, so to get a long-lived particle, you need the right side of this thing to somehow conspire to give you something small, which then leads to a longer lifetime. So you can have, that you can have this matrix element governing the decay and the phase space for the decay. So if you have, for example, compressed spectra, or you have particular symmetries that step in to make things that can conspire to make this right-hand side small, then you can lead to a long-lived particle. And so these long lifetimes in the standard model, like I said, typically arise when you have an approximate symmetry that makes the particle stable. And these same principles generically apply in BSM theories. So what this is interesting for an experimentalist is that this leads to us having to think more critically about how we use the various parts of the detector. So, of course, the observed lifetime of a particle is sampled from an exponential with a shape that's set by its proper lifetime tau, which is often expressed as the proper decay length c tau. And so you can see here, for an example of a c tau of 5 centimeters, you have something like 1% of them that are prompt, 25% in the inner detectors, 60% of the calorimeters, and this is for a kind of an Atlas style detector, 13% of the muon system, and then 1% escape the detector. But if you change the c tau, this changes quite a bit. So if nature has a particle with a c tau of 50 centimeters, then you get 50% in the calorimeters, only 3% in the inner detector, 31% in the muon system, and then 51% escape outside the detector. So as a result, we have to make sure we're using multiple search strategies targeting all the subdetectors of Atlas, CMS, and LHCb, and in fact, beyond the detectors, which I'll touch upon in a moment. So again, what this means for us as experimentalists is in fact a lot of fun. So like I said, these searches have always sort of been considered kind of fringe. And this has luckily changed over the last many years. Not, I would like to think not in small part due to the efforts of people like Giovanna and myself with this long-lived particle community initiative and the LP Bible and the workshop series that we run. I would like to think that we've helped shift the needle a bit, and these are considered much more central set of our set of searches that we do for beyond the standard model physics. And in fact, to the point that I think they back in the day they only made up about 10% of the searches that we did even a few years ago, and now it's creeping up to like 30%, 35% of the searches that we do. So this is a great success. And it's also a lot of fun because it gives you new topologies that are not just, for example, two digets. I love dijet searches, prompt dijet searches, but this is a lot more fun to dive into. And they give you this whole wide variety of wild things. I can't talk about all of these in this seminar, but I'm going to talk about a few of these. And this is, of course, the famous Russell wheel. Heather Russell put together this wheel, and you can find the original plots there at her website. So this is a sampling of the types of long-lived particle searches that we do with Atlas CMS and LHCb at the LHC. I started with Atlas because I work in Atlas, but the story is much more interesting when you think about all these put together. So, for example, we can look for neutral LPs decaying to leptons. So you might think, oh, is this a theory thing? No, this is really just you postulate there's some neutral guy that has a non-negligible lifetime that then decays to leptons in some way, a charged particle, and this means that you have a displacement, right, that occurs where there's a neutral thing before then suddenly having a decay that appears out of nowhere. So identifying displaced charged particles requires the capacity to find tracks with large impact parameters. And so if the LLP decay occurs, say, in the inner tractor, we can use so-called large D0 tracking. CMS has very good tracking for such cases by default out of the box and always has. Atlas previously back in the day, it needed to run a very special, retracking and revertexing routine on a subset of events. And so even a few years ago, it was quite laborious to do an Atlas LLP search, because you would have to have a special filter where you would pick out your events throughout the year. They would go into a special sort of storage, and then after the year was over, they would do a reprocessing of all the data, including yours, so you could finally get the retracking and the revertexing stuff. Luckily, this has actually changed in Atlas, and now because a lot of us made some noise over the years, this kind of large radius tracking is now part of the central tracking we do, which is again a nice success of the initiative to make sure we center all kinds of searches at the LHC. And so both of these approaches require customized triggering strategies, of course, and it leads to a variety of signatures involving one displaced lepton, a pair of separately displaced leptons, et cetera, a combination of prompted and displaced. So in the bottom left here, you can see an Atlas search that gives a nice exclusion for a particular heavy neutral lepton, again, a neutral guy that can then decay to some leptons in the topology C in the Feynman diagram. And on the right is, I like to put this as an example, where you get to see two different displaced particles that are created, and then you get these different displacements that you can search for, that they search for with the CMS experiment, a really nice multi-charged topology. So then, of course, we can also look for neutral LPs decaying to so-called lepton jets. So what is a lepton jet? A lepton jet is not a lepton plus a jet. It's not a lepton minus a jet, whatever that would mean. It's, in fact, a highly collimated grouping of leptons from a low mass, order GeV boosted BSM particle, like a so-called dark photon or a Z-dark. Typically, when it has a small mass, we refer to it as dark photon. Once it gets up to the tens of GeV or so, we call it a Z-dark, a dark Z. And for Atlas, at least, this confounds the standard lepton isolation criterion, and when you have a lot of tracks that are right next to each other. But if you do it, and so it requires a very customized searches. Once you do these, you can end up with some very interesting results. So this bottom left plot is, for those of you that know a little bit about the dark photon searches around the globe, you can see that this is the so-called kinetic mixing parameter epsilon, which is a dark photon. The way you would produce it at the LHC is you make the assumption that it has some kind of kinetic mixing, meaning arbitrarily heavy particles in some kind of loop diagram that connects an off-shell photon to a dark photon that then has to decay back again to an off-shell photon that then decays to, say, two muons or two electrons, something like that. That's the way you have to be able to produce this thing. And most of the lines on this plot are from, say, fixed target machines or Babar up at the top there, and then down at the bottom left, these blobs from supernova data and from beam dump experiments. But then if you make the additional assumption that you can make this dark photon as a part of a non-standard H125 decay, you can start to then say some things about, you can start to put similar plots, or you can start to put lines on the same plots as the other dark photon exclusions. And so this is an example of CMS and Atlas prompt searches, and then combined with the Atlas this kind of long-lived butterfly down here. And so then up at the top right, you can see that LHCb, of course, can get into this. LHCb is that, it's a asymmetric detector. Not enough coffee for me today. And in one direction, and it's designed again to look for long-lived particles, but mostly, standard model long-lived particles. You can easily adapt this to look for long-lived dark photon decays. And they did this as a very nice exclusion in never before covered LLP space, this little island in the white ocean there. And then down at the bottom right, you can see this is a recent Atlas result that's a kind of updating of the long-lived butterfly off to the left, but the rightmost one added a VBS production channel and it extended the mass range a bit. So you can see that this is something we can also search for, the kind of dark photony stuff. We can also look for disappearing tracks. And again, this is strictly topology-based. This is strictly signature-based. So you can have a charged BSM that instead of a neutral one, it can be charged. And in fact, this thing could decay to neutral BSM particle with a nearly degenerate mass and a very low momentum charged SM particle that then curves around the magnetic field and basically disappears. So this is what we refer to as a disappearing track. And of course, I think you know a lot about these. I'll leave the link here too. This is a recent CMS result that sets limits in the context of a particular SUSY model. We can also look for neutral LLPs decaying to so-called hadronic jets. So some kind of a hadronic LLP decay that can happen in different parts of the detector. They require different search strategies. So for example, if it decays here in the inner detector, you can look for so-called multi-track vertices because we have a good inner detector. Yeah, if something decays right in the middle of the calorimeters, this is interesting. You might think, how are we going to possibly see that? But you can look for example, a ratio of the energy in the hadronic calorimeter to the energy in the electromagnetic calorimeter. And if it's a large ratio, that might indicate that suddenly there was a decay that appeared out of nowhere. You can also look directly in the outer muon system. So this is the so-called MS vertex search. And we do all three of these kinds of searches in Atlas. And when you put them together, you have to use, in fact, Atlas CMS and LHCb use slightly different and complementary methods to isolate these signals. This is a kind of older plot, but it gives you a schematic version of the way that these searches are done. And for Atlas, at least, if we combine several of these searches into one place, we can see that, oh, in fact, no, this is just one search, but for different values of the lifetime and different assumptions about the masses here, you can get good exclusions in this, the branching ratio versus the C tau parameter space. So this is one scenario. For example, you can have H125 that instead of decaying to 2 BSM particles that are prompt, they have a non-negligible lifetime that then decay to, say, quarks or gluons or something like that. So this is an interesting thing, because then you start thinking, those of you that might know about some of the Atlas searches that are done, okay, you're looking for say, H125 decaying to some new guy that then decays to, say, jets. So we have prompt searches and we have long-lived searches to where do these searches meet up? And in fact, that's a very good question. And this was the case back in 2018, where you had these kind of rainbow curves off to the right. These are the long-lived searches, and these dots off to the left are the prompt searches. This interesting little curve here is, in fact, where we asked the prompt teams to just not change the result at all, not change their analysis at all, but to very slightly produce one or two more Monte Carlo signal samples, where you give a tiny bit of a non-negligible lifetime. And because we have very, very good B tagging routines, you can get a pretty good limit that's here. But you notice that there's a big hole there, right? So a discovery could be hiding there. So then you flash forward to 2022, and this was the case. People started to get clever, and again, physicists love a vacuum, or I guess physics abhors the vacuum, and so physicists rush in to plug up that hole. And we've started to have some design some searches that are specifically designed to make sure that we're not missing any kind of gap between the prompt and the long-lived. So this is very, very nice. And all of these searches and more will also be pursued and expanded in the high luminosity era. So then it's coming up in a few years. We're going to shut down for a few years and basically soup up the entire LHC to provide a much higher collision rate. And of course, we have to, change the detectors as well a bit. But, for example, in Atlas, we're basically going to rip out the entire inner detector and put in a brand new one. So that's a big, big upgrade. But the size of the detectors is going to stay the same, right? Atlas is not somehow going to get bigger. CMS is not going to get bigger. Otherwise, it wouldn't have the C for compact anymore. So what does this mean? This is interesting because what about very long-lived particles at the LHC? So we can see that we can do these kinds of things in the detector here, but then outside of the detector, we call this a stable particle, right? It goes outside. But then in fact, you can have long-lived particles that are all the way up to this approximate BBN limit. Of course, depending on who you ask, this limit is in various places, beyond which you can't have particles that are longer lifetimes than that, because then they would have messed up Big Bang nucleosynthesis. So you then ask, so this is the outer edge of Atlas. So then you ask the question, how do we possibly get into there? If we can't see something in Atlas or CMS, if it escapes there completely, how are we going to possibly detect this thing? So, standard detectors. So you can think about having dedicated detectors for very long-lived particles at the LHC. So, for example, you can have this. This is a schematic of one of the LHC IP. It's about 100 meters underground, and then you have Atlas or CMS around the IP, the interaction point. And let's say you have a long-lived particle that drifts into the rock and dirt, and then it decays into something that we miss. That's a shame. So you might imagine that in a perfect world, we would spend, billions of euros or francs to, I guess it's on the border, so we'd have to spend some francs and some euros to dig into the rock and build basically 4-pi steradians, spheres of detector material embedded in the rock. This is probably not going to happen. So we do the next best thing. We're physicists, right? We can sample little pieces, assuming that the decays are going to be mostly isotropic. Then we can put little pieces various places away from the interaction point, but outside the volume of the detectors, that will then also be sensitive to some non-zero percentage of these decays. And that will allow us to say some very interesting things with enough data especially. So we do that. And so these are some of the many proposals that are made for these so-called dedicated detectors, or I like to call them uniquely sensitive detectors for very long-lived particles at the LHC. So Methuselah is the one that Giovanna mentioned, which is, I think I'll mention a bit about it in a moment. For time, I'll just kind of leave these here. But there's various ones that are either transverse from the machine, from the interaction point, or more down the beam pipe, so to speak, right? And so you have to kind of have all of these, honestly, if you want to be a full and complete cartographer physicist, right? So if the LHC covers, this is a nice plot from Phil Ilton. If the LHC coverage is in this kind of range here in mass and C tau, then forward detectors like phaser and SHIP, et cetera, they can do this kind of a thing. And transverse detectors have to be here. You really can't do you can't cover everything with one machine or with one project. So very quickly, some of you know about these things. I'll kind of go quickly through these. So you have phaser and phaser new. So this is a smallish about 7-meter long, 20 centimeters wide detector that's about 0.5 kilometers downstream from Atlas that's designed to catch very far forward LLPs that Atlas can't reach. And so this was, in fact, a nice success because it was kind of shockingly quickly approved and installed in time for LHC Run 3 and has already produced results. So here for dark photons, and you can see that these limits that they're getting are brand new, getting into some range already that other experiments have not had a chance to get into yet. And in fact, they've also made a fantastic success in the sense that they, along with SND, which I'll mention in a moment, they have directly detected the first collider neutrinos ever. So the LHC previous experiments have been producing neutrinos all the time, but of course, in the past, the have just said they're neutrinos, we can't catch them, forget it. Phaser and SND have actually detected the first ones ever, so that's really cool. Applause to them. There's also ideas, so there's also something called Millikan, right? So this is a small detector near CMS that's looking for new BSM dark fermions with a very small amount of electric charge. So that's what's millicharge particles. And in fact, the name of the game for these so-called uniquely sensitive detectors, that you find one of the IPs and you find some kind of drainage gallery or an unused tunnel. That's also what Phaser did. That is more or less where you can kind of like draw a line back toward where the IP is, and you put up a little bit of detector material there. So that's what Millikan did. They found this unused drainage gallery. I went there. It was really cool. Even though I don't work on the experiment. And they in fact have a demonstrator that already ran in Run 2, and they got physics results. And this year in Run 3, they have some nice detector improvements and results soon. I'm not sure that they come out already. I've been a bit distracted lately, so I'm not sure if they already came out with their new results. But luckily, this also exists, and it's really fantastic. So I'll just also name check METAL. In fact, METAL is the LHC's first dedicated LP experiment, the first outside of the central detectors. It was already approved in 2010 and it's taking data since 2015. It was originally designed to search for, say, magnetic monopoles that could get stuck. It's a passive detector sitting behind LHCb and highly ionizing particles that could get stuck in the detector material, and then you go and scan later to see if you've seen anything. But there are also some proposed extensions from this team to search for neutral LPs and millicharge particles, kind of like Millikan or things like that, or Phaser. So it's a kind of complementary idea. There's also, of course, these transverse detectors, which you also have to have. Like I said, Codex B is one example. It's a medium-sized detector for neutral LP decays. That's a few meters away from LHCb. LHCb is nice because there seems to be a lot of space around in the cavern there. There's not so much space in Atlas. But in fact, over where Delphi is just sitting and hanging out, there seems to be a space. And the idea is to maybe put some things over, some detector material over there and catch a bit of any long-lived particles that would go out there. The other thing that Giovanna mentioned was Methuselah. And so this is the idea to essentially build a big airplane hangar on the surface. The original idea was build a big airplane hangar on the surface of the Earth above either Atlas or CMS, most likely CMS because there's more space over there, more surface space. And it's kind of changed its ideas over the years. It was, going to be one big box. Now it makes more sense to make it in a kind of modular way where you can, extend it with bigger pieces as you go, with more pieces as you go along. It's currently at both Codex B has a demonstrator that's being built right now called Codex Beta. And then Methuselah is also at the demonstrator stage, which has already taken a little bit of demonstration data, as far as I understand. But also really fantastic ideas. And then I mentioned SND. This is also similar to Phaser at the other side of Atlas that has also detected has detected the first collider neutrino. So that's really fantastic. Then there's something called Anubis, which is a proposal to instrument the bottom of the access shafts covering Atlas above the Atlas cavern, as well as the cavern ceiling, which is really interesting if you think about it. That space is just sitting there. Why not instrument the ceiling of the Atlas cavern? And in fact, they already have a prototype called Pro Anubis that's installed in March 2023, and I think it's currently in commissioning. Maybe it's taking data right now. I'm not sure. So then you think about all these different types of experiments, the transverse ones, the forward ones. If you collect all the forward ones into one facility, that would make things really convenient. So this is the idea for the so-called forward physics facility. And this is a proposal for a new facility about 600 meters from Atlas to house multiple experiments. It's been proposed for high luminosity, and they've already done some things like take some sample cores of the Earth to see what the composition of the Earth is in the place that they want to build it. So that's another really fantastic idea. So then switching a little bit, we don't have just the LHC, right? The LHC doesn't exist by itself. You don't flip a switch and the protons suddenly are going at 13.6 TeV center of mass energy. They go in stages, and you have, in fact, the SPS, which is still creating fantastic beam, and you can use this for projects. And I'll just leave these here for the sake of time. NA64 and NA62 both can say very fantastic things about, and they do great. They have done great searches for long-lived particles, BSM particles that are on those plots that I've shown before. And NA62 is in a hall currently in a hall called ECN3, but it's approved to operate until the long shutdown from about 2026 to 2028. That after that, there's nothing going to happen. So what's going to happen after that? It has an excellent beam. And as some of you probably know, there's this idea for something called SHIP, which is the search for hidden particles. It was originally proposed as a new standalone facility that was going to cost a lot of money, and now it's a newly approved beam dump experiment in this space. So another good example of physicists being, being inventive about space and changing and adapting to make sure we can maximally use all the stuff we have. So that's really nice, and it's nice that that's going to go along. And then, of course, the SPS also gives a bunch of other particles. Gives protons, which you can then turn into other beams of things. So, for example, we have protodune that's in EHN1, the largest building at CERN. If some of you haven't been to the Prevision site to check it out, it's really cool. Of course, protodune is a prototype for the Dune experiment, which is going to be built in the United States, a big neutrino experiment. But you have these large cryostats sitting there. You fill them with, I guess it's liquid argon, right? You can use them for BSM searches. So these are going to be, in fact, used. These are going to be been proposed to use as a beam dump facility to search for BSM LPs like HNLs, dark matter, millicharged particles, etc. And in fact, they have proposed sensitivity or projected sensitivities for, say, 6 months of running that can start to say things that can start to get into some area that, this map making idea that other detectors haven't gotten into yet. So that's a really good idea, again, to use something that already exists. It's a worldwide program. For the sake of time, I'll skip these. There's, interesting things going on at Fermilab and also in Japan. And it's a broad international effort. And so just keep in mind, right, that, LLPs are this, it's generically well motivated. It's something that we need to look for. Otherwise, we're bad physicists. And it's nice that the entire world has come together, the global physics community, to recognize that these are important and to put significant efforts and resources toward them. And again, to put a very fine point on it, this is what I mean by cartography. So these are some of the summary plots from our FIPS 2022 workshop report. And if you put these all together, you can see a lot of these that I didn't even mention here. It's a worldwide search, and it has to be a worldwide effort to make sure that we're not overlooking anything. So just to finish, I want to say, think about the kind of future of our field as well. Right. So we have, proton synchrotron back in the day was like a big deal back in the 1950s, right? It's 628 meters around. That probably seemed enormous as a particle collider for people of the day. But if you go back even farther, discoveries were made. Basically, anytime, physicists built a bigger machine, they ended up discovering something, right? So, for example, back in the 1890s, Thomson by himself on a table in Cambridge could discover the electron. And then, of course, we had the proton synchrotron, which was in the 50s. But then you jump forward to the 60s. You had the alternating gradient synchrotron about 800 meters around, 33 GeV, which led to, for example, the proof that the charm quark existed. Yeah. And so then you had, when you went to something even bigger, the SPS, 7 kilometers around in the 1970s, this led to the discovery of the W and the Z bosons. Then, of course, the Tevatron, right, which was similar size in similar size range to the SPS, also led to the discovery of the top quark, right? Then, of course, the Large Hadron Collider was a big step forward in terms of size. LEP, of course, was in there before, made some fantastic measurements of the W and Z, things like that. But then you put in the LHC, suddenly you discovered the Higgs boson. So we start thinking about what's the future of the field, what's going to happen at future colliders. Like I said before, we're out of hints. Anything could happen at the future colliders. And in fact, there's no one, well-motivated size of detector and energy and collision energy of the energy frontier detectors to build. None of them are any more well-motivated than any other. But, for example, the Future Circular Collider. So presumably when the future becomes the present, we'll change the name. But for right now, it's called the Future Circular Collider, which is going to be about 100 kilometers around. And the LHC will then be a feeder into the the FCC, right? And that's a fantastic idea. And so, and the key thing to think about is that when this goes forward, when the FCC, if the FCC is finally approved, it has a lot of momentum behind it now, but there's still a lot of work to do to make sure that funding can be in the right places, et cetera. People are thinking already in advance to make sure we don't leave out things like long-lived particle signatures, because there's been a lot of work. It's been a lot of fun work over the last 12 years, but these were not really, Atlas and CMS were not really thought of as going to, as being sort of long-lived particle detectors when they were built. But so we had to do a kind of like a lot of hacking and a lot of making sure that we're not missing things. If you think about this farther in advance, then and make sure you're not going to leave this out when you say design detectors for the FCC, you're way ahead of the game. So there's lots of studies that are already going on for, and not just at the FCC, other things. So for example, for CLIC and for other detectors and other linear colliders, there's ideas that are going around. So this is on the right here. This is a study for disappearing tracks at a future muon collider. Some of you have heard about this idea of a muon collider as well. And this also would be great. Make sure we're not leaving out the lifetime frontier in any of these projects. So then, of course, what's beyond that? Okay, we don't know. Yeah, there's also a similar idea, something that could be proposed to happen in China, which would be a similar size, to the Future Circular Collider in the same, range to kind of jump up in energy. But again, like I said, there's nothing magic about 100 TeV. There's nothing magic about this, right? It's just it's a good jump up in energy. We have to look there. Otherwise, we'll never know what's there. There could be discoveries there. And even if we don't see anything at the FCC, it'll be a fantastic discovery because we're measuring parts of the standard model that we've never seen before. Fantastic discovery, has to be done, cartography physics. But what's beyond that, right? You think about, there's a proposal by some colleagues that are at, I think, Texas A&M or something like that. I think the proximity to the Gulf of Mexico made them think, we could find a spot that's neutral buoyancy in the Gulf of Mexico, and we could have a so-called collider in the sea. And there'd be 1,900 kilometers around. It could reach, say, 500 TeV. Okay, this is a very interesting idea. But again, there's nothing magic about 500 TeV. What about if we think really big? What about if we think, what about if we were to build something that was, say, 1,000 times the energy of the LHC that could reach 14 PeV? And where could we do this? I mean, if you try to find a place on the Earth where you're going to build an 11,000 kilometer tunnel, it's going to be tough. You could do it. There are places on say around Asia, but you would have to go, say, underneath all of China and also Russia, and also go underneath some enormous mountains. It's probably not going to be worth it. So why don't we build this on the moon instead? And if you think that I'm joking, I'm not really, because just a couple of years ago, I published a paper with Frank Zimmerman about this idea of a very high energy hadron collider on the moon. Turns out there's no showstoppers to happen to build this. And in fact, when I talked to 95% of colleagues in our field, when they saw this paper, they're like, "That's amazing. I hope I'm alive when this happens." But when I talk to people in the space industry, because I speak around the world at various events, when I talk to people in space and things like that, they're like, "Oh, let's collaborate. We're gonna do, let's do a proposal for DARPA. I'm working on self-assembling structures in space, things like that." So they're very into this kind of a thing. But of course, let's think about where the next guaranteed discovery in physics is. I said there's no big hints. In fact, I was lying. We all know this. There's in fact one big hint left, and it's an enormous one. What I really want is a collider that reaches the Planck scale. But this is not just 1,000 times the LHC. This is 10 to the power 16 TeV. And by some estimates, of course, to reach such a thing, we would need to build a collider that circles around the outer orbit of Neptune. So this is probably not going to happen in our lifetimes. But in fact, Frank, speaking of which, he thinks that maybe I'm being a little bit pessimistic when I say this. He thinks that we could reach the Planck scale. Potentially, it's something much smaller that would circle around the sun about 1/10 of the distance between the Earth and the sun. Still quite outside the realm of current capabilities, but much smaller. So I say all of these things just to really, really underline the point that just because we don't have a big golden hint for a discovery right around the corner at the next machine, or the next amount of data that's being taken, or the next precision measurement, that in fact is completely missing the point of what particle physics is. We are in a brand new era of particle physics. And we have big open questions, but no big obvious hints. This is not scary to me. This is, in fact, really kind of exciting because it means that we can recapture the spirit of exploration. So we can embrace and celebrate the fact that experimental collider physics is cartography, and that's a good thing. We really need to look everywhere. It's kind of like astronomy. Honestly, if you think about it, a lot of the discussions of, say, the FCC and things like that, you'll have people that will eventually say, well, it's hard to motivate, without a kind of, clear plan as to what we're going to see. Well, our astronomer colleagues don't have to do that. Like when they talk about a new big, a telescope, they don't say we want to build this telescope because we want to look at that one galaxy right there and nothing else, and because we think aliens are going to be there. That's not what they say. So we shouldn't have to say that again. They say we need to look at parts of the universe that we've never looked at before. That's the same thing with particle physics. If we don't look in future and higher energies and different machines that can do different precision measurements, we'll never know what's there. So that means that, in fact, for the next few years and decades, particle physics is going to be very exciting because it's going to be interesting to see what kinds of innovations take place to really make sure that we're not missing the big discoveries at the LHC. Again, there could be discoveries that are, this high luminosity era that's coming up. We're going to take something like 15 to 20 times the data we've taken now. There's still plenty of space for new discoveries to show up, but also at future colliders, it's going to be interesting to see what happens. So I'll stop there, and thanks for your time.
Thank you, James. I really enjoyed this talk. Are there any questions from the audience?
Yes, I do have a question.
Yes, Tesio, please go ahead.
Many thanks, James. Very nice talk, very nice overview on the collider searches at the LHC and LMPs. Can you comment a little bit more about this Millikan experiment? I've never heard about this. It's just search for milli-charged particles. What is this about?
Yeah, so it's a search for milli-charged particles, and you can naturally get you can get new sort of dark fermions in a lot of different models where you naturally have some kind of extremely light guy that shows up with a tiny fraction of the electron charge. So if you make this very, very simple assumption that you realize that the kind of the MIP energy at the LHC experiments like ATLAS and CMS, it's never going to see these things because it's not enough. The charge is not enough to fire our detectors. So instead, you have to design something that has a very, very low threshold. And what they did with Millikan, like I said, is they were looking around for some place near, not too close to, but some distance away from one of the interaction points of the LHC, where they could put together some detector components and point them directly toward the interaction point, so that if you have milli-charged particles that are coming out, you would eventually see them. So that's what Millikan is. And like I said, there's other ideas. This idea has been adopted by some other groups that want to create one for metal, which is called metal map now.
So the key point is threshold.
Yeah. If I have literally a charged particle, but it has a millicharge and it goes through like the straw tubes of the LHC, it's not going to fire them. It doesn't have enough charge.
Okay.
Oh, Atlas.
If I may ask another question, you mentioned some proposed experiments. You mentioned that SHIP has been approved.
Yeah.
Right. And what's the status of Methuselah?
So Methuselah is still at the proposal stage and kind of demonstrator stage. It also has I'll be honest, it faces a little bit of an uphill battle, and because it's a little bit more expensive than some of the other proposals, right? I mean, it's a very good idea because you need, and I support it 100%, but you need an enormous volume, a relatively large volume on the surface of the Earth, and that gives you a really decent size of exclusion that you could get, or sensitivity to these new discoveries. However, when you look at what the budget is compared to some of the other ones, the sort of, again, it's hard to put an actual metric on this, but the potential discovery versus the discovery to euro ratio is not as, if you squint just in a certain way, it's not as high as some other ones. So it got not so much of a super favored result in the SNOMAS process. it was considered a potentially good idea if it could sort of scale down its scope a bit. So it's not, like I said before, it was really designed, it was, the original discussions back in the day, Giovanna probably remembers this, is David and people talking about building an airplane hangar on the surface of the Earth, and you put some RPCs or something on the ceiling. But that's going to be too expensive. And then, so they started thinking of different ways that they could do it. And now it's more of a modular idea, where instead of a big airplane hangar or a big contiguous object, you build, say, columns that you can extend. Say you have budget for 10 or 20 of them for one year, then you can get budget for more of them and add capabilities in the future as well. So it has not been approved, but it's still the proposal stage.
Thank you.
More questions for James? I have a few. James, you mentioned about these forehand and delight experiments for FCCHH. Are those lifetime frontier detectors that are being proposed?
No, I think these are, where my slides go? One moment here. My slides disappeared in the Zoom thing. Did I just get rid of them completely? I think I did. Hold 1 second here.
No worries.
Yeah,
this is also, I've never heard of these names before.
Yeah, so Delight and Forehunt are two different proposed detector designs for the FCC-HH. So this would be far, far in the future. And as most of you know, the FCC, the proposal would be to run, an E plus E minus machine, to do precision measurements of the Higgs and Z and things like that. But then the second stage would be to do a Hadron machine, and that would not start until 2070, so the soonest. But people are also already thinking about detector designs for there too. And if I remember correctly, both of those are detector designs for specifically for FCC-HH that are also making sure they're not going to be not sensitive to long-lived particles.
I see. So these are the analogs of the IDEA detectors.
Something like that. Yeah.
FCC-EE. Okay.
Exactly.
Nice.
Exactly.
Yeah. Francisca.
Hi, can you hear me all right?
Yes.
Okay, perfect. Sorry, it's not just that my Wi-Fi is kind of slow. So, James, thank you very much for your talk. I really want to steal the the diagram of the accelerators at the end, so I think it's very good. I work in Atlas, and I have a question or maybe a feeling from you, because you mentioned that over the years, Atlas has now realized that they need to start saving, for example, displaced activity in different parts of the detector. So triggers are changing, combined performance groups are changing, etc. But you mentioned an example about tracks, for example. So I know that in the inner detector, there's a lot of movements on displaced activity. But do you know what is happening, for example, in the calorimeter displaced activity or muon system? Because at the moment we are on a trying to do an analysis where muon performance group is not just let's say studying displaced muons, so it's kind of a problem. So do you have a feeling about the other systems?
Yeah, so for the calorimeters, I can't speak for the hottest and latest, but I know that the people that I've had talked to over the years, they're aware that there's a lot of interesting things you could do with the calorimeters. In fact, even with the existing designs now, not high luminosity era, but current era, people have been thinking about how you could use the tile calorimeter, to do some more kind of granular measurements, and maybe you could be more sensitive to displaced decays, etc. And so I don't know what the plan is for high luminosity, to be honest, for phase 2, but I know that they're thinking about it. I don't know what the idea is in terms of having combined performance efforts to that. I think maybe we should get together and make sure that they're not overlooking that. For the muon system, there's a lot of work that's going on. I can't speak. You probably have more experience than I do right now with trying to get information out of the combined performance groups. But I do know that for phase 2, for high luminosity, there's a lot of work that's going on to make sure that we're not going to leave out displaced signatures, even at the trigger level in the muon system. So I'll give you one example. In fact, I'm working right now on just starting a project with some people to look at how we could, in fact, have level 0 triggers. So this is like putting some kind of machine learning techniques on FPGAs specifically for the muon system in Atlas, specifically for, say, so-called exotic or long-lived or displaced signatures. This is still in its infancy, but there's a lot of idea to have. Right now, people have already done lots of work in Atlas for standalone L0 triggers, only using, say, the MDTs, the drift tubes, which have better precision. But then we're currently working on adding machine learning, taking advantage of, say, CNNs or something like that, and then using this to make sure we're not leaving out even displaced signatures. So this is still just a project that's just starting right now, so we don't know how successful it'll be. But just to demonstrate to you that people are definitely thinking about this, and I would be very surprised if it falls by the wayside for high luminosity era for phase 2. So hopefully that's good news.
Great. Yes, great to know. Thank you.
Any more comments or questions? Marco Aurelio? You are muted.
Yes. Okay, now I'm fine. Thank you, James. You mentioned that Higgs to invisible decay is about to 10%, and it will be hard to diminish it. What number are we talking about?
That's a good question. I think that changes a little bit when people do new estimates of the kinds of searches that we can do for the high luminosity era. Someone here might know better than I do what the current estimate is for even the eventual limit that the LHC can give. But my understanding from several years ago, there was never going to be more than, say, 2 or 1%, a few percent. You'll never get it smaller than that over the entire run of the LHC.
Okay. Thank you.
And that, of course, is a shame. And well, not a shame, but that's, of course, one of the big motivations for the next generation of collider being a Higgs factory, right? Because the Higgs being this very bizarre or very unique particle compared to all the other ones in the standard model has this very, very narrow decay width, and which means that you could have things show up in that in the branching ratio down at the 10 to the power minus 3 level that could still be BSM decays that we would have to measure. So again, we just have to build a Higgs factory. We can't possibly make enough of them even over the entire run of the LHC.
Oh, I see. Thank you.
So following up on that, James, you mentioned all these anomalies at the beginning, right? G-2, W mass. Which one do you think by the end of the entire run of the LHC we will basically narrow it down the most, or the one that you could say, this is the one we should focus on the most after, like post LHC? Yeah,
well, these kinds of so first of all, I mentioned a few of these kind of possible resonances in whatever spectra. Those are going to come and go always. So either one of those is going to turn into a peak, or it's going to just go away with more data. So those ones, I think they'll be either verified as a the kind of the inverse of the X750 saga, right, where it was a little bumplet and then it turned into nothing. Maybe it will turn into an enormous thing, or it'll just go away like X750 did. And so those ones, it's not like they're motivated or anything in terms of from a theoretical perspective. For the W mass, again, I think that the W mass saga is very interesting because this is a real, measurement from the Tevatron. But the truth is that both Atlas and CMS, when they see that, we're going to say, okay, let's do extreme precision just to be able to, to verify or rule out. So that's either going to, and I think it's already a little bit in tension. Most people are thinking, what was going on with the new measurement from the Tevatron. There must be something kind of askew there. And in terms of the other ones, it's hard for me to say. I don't know if I could even say, from a first principles perspective, which one of these should be paid attention to more than any. I really think that, like, my idea is everything has to be searched for.
I know the ones that survive, basically. This is
for sure. Well, that's what cartography is, right? If someone tells you, it's like, I was up in the middle of the night and I was sleepwalking over in this corner of this corner of the field, and I think I saw a neon green alien, And then you come back and you're like, well, okay, I guess we can look there. Where they go over and look and it's either there or not, right? You have to look because this person is credible, but then they come back and it's okay, there's nothing there. So I think that everything really has to be looked for. Otherwise, we're doing ourselves a disservice, which is also kind of interesting too, if you think about it from an operational perspective, right? The budgets in our field are not going up exponentially, right? I mean, they're stagnating, if not, going down. We're not going to have more people to do all of these searches. So we're going to have to get cleverer about those that, that survive in the field. They're going to have to become cleverer about utilizing more, automated anomaly detection, which in fact people are thinking about now, both have been thinking about for a while, but they're thinking about in earnest more now about both the so-called offline after we take the data, and also at the trigger level too, doing more anomaly, automated anomaly detection. So I think that this is an interesting commentary, social commentary about our field too. It's not expanding. That's not going to expand in the same proportion as the amount of data that we're going to get in the future. So we need to be clever about this.
Yes, absolutely. Okay, if there are no more questions for James, I think in honor of time, we can finish. Thank you so much, James, for this wonderful talk and very interesting discussion.
My pleasure. Thanks again for the invitation.
Okay, and see everyone at the next webinar.